Hello guys, we're going to have a look at anti-differentiation of circular functions in this session, so fasten your seatbelts. It's easy. Now you know, ladies and gentlemen, that if y equals sine of kx plus a, what is the derivative of that? Think about it. Yes, it's k times cos of kx plus a, and we know that this k term here is a result of doing the chain rule. Okay, we know that the derivative is cos of the thing times the derivative of the thing in here, which is k. Yes? Okay, this is the chain rule as I just said. Hence, ladies and gentlemen, if we went backwards and anti-derived this derivative, then we get back to our original function, wouldn't we? Plus c, of course, don't forget the c. But on the other hand, if we were just anti-deriving cos of kx plus a with respect to x, without the k in front, okay, then we would have to make this term here, the antiderivative, with a 1 over k as a kind of reverse chain rule thing happening, because if you think about it, if I derived this with the 1 over k, it would be, what would it be? 1 over k times cos of kx plus a times the k from the chain rule, which would then be completely neutralised by this 1 over k, and you wouldn't have a coefficient in front. That's the idea of it. It's reverse chain rule, okay? You get it, don't you? Similarly, we could do the same thing if y equaled cos of kx plus a. We know that the derivative would be k times minus sine of kx plus a, and therefore if we went backwards and anti-derived our derivative, we would get back to the original function up here, plus c of course. But if we anti-derived this derivative without the k in front here, we'd have to put 1 over k in front of here to reverse chain rule, the effect of deriving this to get that, you see, without the 1 over k, of course, we would get minus k sine kx plus a, wouldn't we? We would indeed. So it's a reverse chain rule operation. When anti-differentiating, we divide by the coefficient of the x term where you see a kx plus a or a kx in the vital spot. Okay? Alright, here it is in all its glory. If we're anti-deriving sine of kx plus a with respect to x, we get minus 1 over k times cos of kx plus a, plus c of course. And if we're anti-deriving cos of kx plus a with respect to x, we get 1 over k times sine of kx plus a plus c. Reverse chain rule. Just divide by the coefficient of the x term in this bit in here, behind the cos or behind the sine. Okay? You get it, don't you? Alright, we're going to do some practice now. Find an antiderivative. Now, did you see the word an, antiderivative? I deliberately put that in because they often do that in questions that you are asked, and it really means a specific antiderivative, not the general antiderivative. So in this case, you're allowed to not put in the plus c if you like, because you're just asked for a specific case, not the general case, which must of course include the plus c. Alright, let's go for it, guys. Now, come on, get your neurons firing. What's the answer to this? Well, I can give you a hint. It's going to be cos, isn't it? Well, it's going to be minus a half of cos of 2x plus pi on 3 plus, of course, the c. Okay? Now, where did that half come from? Well, it came from here. We had to reverse chain rule, didn't we? All right, excellent. Now, I've just given you a great big reminder there that you don't have to put the plus c for an antiderivative, but you do have to put it for the antiderivative. Okay, so I've just emphasized here, it is not wrong to include it if you do include it, but it is wrong to not include it for the antiderivative, which means the general case. Okay, I can't emphasize that enough. Okay, so if you just want to put it in for safety, that's fine. Number B, okay, what's the answer to this one? Come on, get your neurons firing again. Well, it's going to be a sine, isn't it? Yes, so it's going to be 1/5 of minus a fifth of sine of minus 5x plus c, isn't it? Yes, did you get that? So the final answer is minus 1/25 of sine of minus 5x plus c. Are you having fun? Of course you are. Example 2. Now we've got some definite integrals now, which means we can definitely do them, can't we? Now, the first one, it's a sine, so the answer therefore is going to be minus cos, and we have to divide by 3. So here it comes. There it is. Minus 1/3 of cos of 3x plus pi on 4 evaluated between these two terminals. Note the square brackets, and the way we do this, we put the terminals on the right hand end of the bracket, then we evaluate the whole expression here with pi on 4 substituted for x, then minus the whole thing where 0 is substituted for x. Yes, of course, but it's already got a minus out the front. So that's going to change the plussing and the minusing a little bit, but we can handle it, can't we, guys? We certainly can. Now, let's go. What are we going to get here? We're going to get, with the pi on 4 substituted in, we're going to get minus 1/3 cos of 3 pi on 4 plus pi on 4, which gets us pi. Then it's going to be plus instead of minus because of this minus out the front in the first place, plus 1/3 of cos of 3 times 0 plus pi on 4, and we're nearly there. What's cos of pi? Come on, someone from the audience, yell it out. Cos of pi? Yes, minus 1. So therefore we've got minus 1/3 times minus 1, which gets us plus 1/3, plus 1/3 times this, which is 1 over root 2, which of course you knew, didn't you? And here comes our final answer. Now, I've just rationalised that this little beastie here, but you don't have to do that. And if you do it and get it wrong, well, that's a tragedy because you lose marks. So I'm not advocating that you rationalise denominators, but I am advocating that you put them in a simple form, which doesn't need obvious simplification. Okay, so if this was, say, for example, 2 over 6, you'd have to make that 1 over 3. Otherwise, I think you'd be getting it wrong. All right, let's go. B, for you and me. Come on, what's the answer to the antiderivative of 1/5 of cos 2x? Well, the 1/5 is already there in the first place, so that just goes along for the ride. But come on, what's the antiderivative of this beastie? Now, did you notice there's a mistake here? What is the mistake? I deliberately put this in to make you think. What is the mistake? Yes, I just fixed it, okay? I missed out the dx, which is absolutely really bad, and if you do that, they will take marks off you as well. Okay, so don't go doing that. It's very, very unfortunate. So here we go. The answer to that is going to be, let's think about it, it's going to be 1/5 of a half of sine 2x plus c, evaluated between minus pi and pi, so it's 1/10 of that. Now let's just go for it, should be pretty easy. So 1/10 of sine 2 pi minus 1/10 of sine of minus 2 pi, which is going to be 0. My goodness, it's 0. How amazing. Alright, let's keep going. We've got another example here for you. Find the area of the region indicated for each of the following graphs. Looks like we've got y is sine of x over 2, and we are required to give the area under the graph where x goes from 0 to 2 pi. So it's from here over to here. Okay, so it's an area question. So we must make sure we get a positive integral because areas can't be negative. So there it is, shaded in for you. And we have the area will be from 0 to 2 pi of sine of x over 2 with respect to x, okay? And if you anti-differentiate that, you'll get minus 1 over a half, which comes out to be minus 2 cos of x over 2. And we don't need the plus c because it's a definite integral that we're doing here. And we're going from 0 to 2 pi, aren't we? Okay, so that's pretty easy. It's going to be minus 2 cos of pi plus 2 cos of 0, okay? You get that, don't you? Now, what's cos of pi and what's cos of 0? Can you think? Yes, that's good. So cos of pi is minus 1 and cos of 0 is 1. So we get, really, we're getting 2 plus 2, which is 4. How marvellous. All right, do you get the idea? It's an area question, so make sure the integral is going to come out positive, all right? Another one for us. This is part B, where we need the area under the graph for x goes from 0 to 2 pi. Well, this is a bit of a wobbly one, isn't it? Good grief. So this is really what we need, except we need areas. Now, that would be a fatal mistake to do just an integral of that, because this hump and this hump are under the x-axis. And if we were integrating in that direction, in the positive x direction, these integrals would come out negative if we integrated from pi on 4 to 3 pi on 4 and from 5 pi on 4 to 7 pi on 4. So we've got to do something to fix that up, okay? Yes, you know it, don't you? So what I did was, I thought, what's the easiest way out of this? Because it could be a complete nightmare. And remember, in exams, you don't have a lot of time. You've got to think smart, okay? So by symmetry, I can say that the area is 4 times the area of this hump, because there's the equivalent of 4 of them. There's 1, 2, 3, 3.5, 4. So that is going to save us one heck of a lot of grief and a lot of calculation and misery trying to work that out if we just do it that way, which is a nice, smart way to do it. I'm sure you'd agree. 4 identical humps. So we get that. We get the antiderivative. Now think about that. Is that right? Antiderivative of cos 2x is, yes, it's a half of sine 2x. 4 times that between there, and it just becomes a simple matter now to evaluate it. See if that's right. Is it right? Yes, it looks pretty good. Yes, it does. So therefore it's going to be 2 times 1, because sine of 5 over 2 is 2.5 pi, which is just the same as half of pi. And this beastie over here, sine of 3 pi over 2, is in the negative, yeah? So that's 2 times minus 2 times minus 1. So we're going to get, what are we going to get? 4. How wonderful. All right, now, alternative methods for you to consider. I just gave you one. Of course, if you went like a lamb to the slaughter and did it the dreadful way, like that, you'd be forever calculating and going quite mad in the process and probably making mistakes. But you'll notice that I've got a minus here for this hump, so that I'm minusing what would already be a negative integral. So to make it positive, and I'm minusing this one here, this second hump here, which would make the negative integral positive. So I'm ensuring that every single one of these integrals is positive, okay? But it's one dog of a way to do it, if you don't mind me saying so. Comes to 4. Of course, if you didn't want to put a minus there, you could leave a plus there and just reverse these terminals, okay? You'd go from 3 pi on 4 to pi on 4. In effect, you're going backwards. So negative x, negative y, positive integral. That would do the same thing. Now, there's also, yeah, I know, too much work, too slow, you said it. Now, part B for you and me is, if you do it this way, this is the most beautiful way of all. If you had a CAS calculator, this means that you're just doing the absolute value of this function. Now, I know that absolute value is off the course, but it's jolly useful. So it simply means we're only taking positive values of y. And if the function has a negative value of y, this modulus sign effectively turns it into a positive value. So in effect, it flips the negative parts of the graph into the positive and saves us all a lot of trouble. Just like that. Isn't that wonderful? So it's a beautiful thing to know about, guys. And you just get 4, okay? Yes, if you had CAS, that'd be truly marvellous. And I've got a couple of examples of CAS over the screen here. There's one. That's the first way we did it. That was the smart way, okay? We were just going from the middle hump, from 3 pi on 4 to 5 pi on 4, and 4 of them. And we just go like that, and look at that magic calculator, yeah? And this is the other one. This is the absolute value one. It's pretty marvellous. All right, that's it. Hope you got something out of that, and we'll see you next time.